Have you ever wondered how we can measure the radius of a curved surface without knowing its center? In this video, I'll show you how to calculate the radius of curvature using a simple instrument called a spherometer with surprising precision. We'll measure just a tiny height difference, and from that, determine the full radius of a sphere. Let's get started. We will need a spherometer, a convex spherical surface, a flat surface, and a sheet of paper. The convex spherical surface is shown here, and the small letter r represents the radius of curvature of this surface. We can calculate it using the Pythagorean theorem in this right triangle, based on the following relationship. We determine the distance ρ from this diagram, where h1, h2, and h3 are these three outer legs of the spherometer. These legs form the vertices of an equilateral triangle. Because of that, the distance ρ, which is the distance from the center of the triangle to one of its vertices, is equal to a divided by the square root of 3. And from these two relationships, we obtain the final formula for the radius of curvature of the convex spherical surface. Now let's look at the last unknown quantity, the small h. This corresponds to the vertical distance shown here in the diagram. This point represents the central screw of the spherometer, and this is the convex spherical surface. If we record the position of the central screw as h1 when it touches the top of the convex spherical surface, and its position as h0 when it touches the flat surface, then the difference h1 minus h0 gives us the value of h. So the distance h is the difference between the central screw's position when it touches the curved surface and its position when it touches the flat reference surface, which would correspond to this dashed line if the spherical surface were not present. This means we must measure the position of the central screw in two cases. First, when it touches the flat surface, and second, when it touches the top of the convex spherical surface. The difference between these two positions gives us the value of h. We determine position h1 by slowly rotating the spherometer screw until the entire instrument begins to pivot around the central screw. This indicates that the central screw has made contact with the convex spherical surface. We determine h sub 0 in a similar way. This time, the spherometer is placed on a flat surface. We rotate the screw until the instrument starts to pivot around the central screw. When that happens, we know the central screw has touched the flat surface. Here is shown how we read the position h1 and h0 on the spherometer scale. Here, the reading is exactly 10.00 millimeters. As we rotate the scale further, we obtain 10.05 millimeters. After 50 divisions, we reach 10.50 millimeters. At this point, we've reached the mark below 10, which corresponds to half a millimeter. Continuing further, the distance increases. Here we have 10.70 millimeters, and here we reach exactly 11.00 millimeters. Finally, to determine the distance a, which we need to calculate the radius r, we press all three legs of the spherometer onto a sheet of paper. After lifting the instrument, 3 points remain, forming the vertices of an equilateral triangle. We then measure the distance between these points, the value a, using a caliper. If you haven't seen my previous video on how to read a vernier caliper, make sure to watch it next. It explains exactly how to measure this distance with 0.02 millimeter precision. And that's how we determine the radius of curvature using a spherometer, by measuring just a tiny height difference and applying a bit of geometry. If this helped you understand the concept, make sure to hit the like button. It really supports the channel. Subscribe for more physics and measurement tutorials and turn on notifications so you don't miss the next video.